Thank you so much for showing up tonight. This is a really fun event. This is the first time I'm giving Astronomy on Tap up here as a speaker. I've been here in Austin for about a year, and this is really one of the best endeavors that I think is associated with astronomers here in Austin. We have a big hub of astronomers, so it's really fun to be able to engage with the public this way. So today I'm going to tell you about imaging exoplanets. I know that after last week, some of you may want to be living on another planet. So please follow along closely, and I'll tell you the status that we're at in terms of finding habitable exo-Earths. So this cover image here I really like. This is what we really want to do in the field of exoplanet imaging. Right now we're in the super Jupiter regime with basically being sensitive to masses greater than about 1 Jupiter mass. Ultimately, what we want to do is take an image like this of a planetary system with terrestrial planets and to be able to characterize the atmospheres of these planets. So I want to start off with this grainy photo. These are actually 2 cameras on board Voyager 1 looking back at the sun. So this is the sun here. We have 2 high-resolution images here. When we zoom in on one of them, you can see a tiny dot inside this sunbeam. This is an internal reflection here inside one of the cameras. That dot is the Earth. Again, this was Voyager 1 at 40 AU in 1990. It was launched in the late 70s. After it was done with its main mission of studying the outer gas giant planets, for no scientific reason other than to provide some perspective, it turned around and took a photo of Earth. This is the famous pale blue dot image that Carl Sagan really helped deliver. And I really like this because in addition, again, to some perspective on Earth being just a couple pixels here in diameter, this is really what we want to do in the exoplanet imaging regime. We want to be able to find planets like this around other stars, which will be basically point sources like that, and study their atmospheres from afar. So we know a lot about exoplanets. Over the past 5 years, one of the biggest results in the field is that exoplanets are everywhere. Every star, on average, has at least 1 planet, and the frequency of rocky planets is incredibly high. So this is basically the size distribution of planets and their probability of finding them around a star. So gas giants are relatively rare, but Neptune-sized planets and below, especially mini Neptunes and super Earths, a little bit larger and more massive than our own Earth, are incredibly common. So the point here is that rocky planets, the frequency of rocky planets is not 0.1%, it's not 1%, it's of order 20%. It's incredibly high. So where we want to transition in the field is, over the long term, the vision for NASA and the exoplanet community is beyond simply finding planets. Now we want to study the atmospheres of planets, study their chemical compositions, weather, cloud patterns. Eventually we want to turn to habitability to study whether or not liquid water exists on the surfaces of these planets so that they're not too close and not too far from the host stars that they orbit. And ultimately to answer some basic questions about life on Earth, how life evolved and originated, by studying how common it might be around in other planets. And one of the ultimate goals was led by this man here, who is very commonly depicted on the History Channel. And so while this is a joke, it really is the search for biosignatures that's driving a lot of the motivation in the exoplanet community. So I just want to outline a few of the challenges that we face to actually image planets. The first is the angular resolution of a telescope, okay? So when you turn a telescope to a star, the star is basically a point source, and what you get in the telescope is this thing here called a diffraction pattern. The bigger the diameter of the telescope, the tighter this diffraction pattern is, so it gets more compact. To be able to image a planet or a star next to another star, you need a telescope diameter that is capable of resolving these two. So in terms of sort of nearby stars and probing sort of planetary separations, about 1 AU separations, the mean Earth-Sun distance, we need telescopes that are very large on the ground, of order 8 to 10 meters. The other feature of planets that makes them very difficult to actually image is their brightness relative to their host stars. So this is a plot showing the relative brightness on a logarithmic scale of planets in our own solar system as a function of wavelength. Now, there are two components to the spectra of planets. One is a reflection spectrum. So when we go out at night and you look up and you see Mars or Jupiter or Saturn, that's reflected light from the sun bouncing off the planets and coming back to us. If you go into the infrared, you can get, there's another sort of peak here that's due to thermal emission. The planets have some temperature, so this is black body emission. So when I look at everybody in the crowd here, and you're looking at me, we see reflected light. If we go into the infrared, I would see all your bodies glowing warmly against the cold background. That's the same kind of two-temperature feature here. So if we're trying to image planets in the optical, where there are a lot of interesting features that we might want to study in their atmospheres, at least for the Earth-Sun system, the contrast ratio, or the brightness ratio, is of order 10 billion, 10 to the 10. It's incredibly difficult to image these kind of contrasts. And finally, we're dealing with an atmosphere, a turbulent atmosphere, which is something that is not romantic to astronomers. It's not interesting. It makes stars twinkle. So it's as if we're at the bottom of a pool looking up at essentially a candle or a flashlight that's going to move around a lot because of air pockets, which have different indices of refraction, and they scatter light in different directions. So the twinkling of stars is the bane of our existence in astronomy. That's what we want to get rid of. So we can either launch telescopes into space, or we can somehow correct for that. So the answer, again, the solution to this, at least for now, is using the largest telescopes on Earth, 8 to 10 meters in diameter. It's using something called adaptive optics, which was a technology developed by the military and declassified and now used in astronomy. So this is a way of, in real time, measuring and correcting for the turbulence in the atmosphere. So here's just an example of with adaptive optics off and with it on. You can basically get diffraction limited images. In this case, this is a very close binary. And likewise here for, I think this is Uranus. So we use adaptive optics to essentially bring these massive telescopes into space. But that's not the end of the story. AO is never perfect. So we have to also incorporate a lot of post-processing. So this is what I spend most of my time doing, is developing signal processing methods to get rid of the residual uncorrected light from these host stars to try to bring out faint point sources like this planet here. So we've imaged a number of planets. My favorite is the HR 8799 system. How many people have heard of that? A few people, okay. So this is a massive star here. These are the residuals after trying to remove as much light from the host star as possible. And what it reveals are 4 gas giant planets labeled B, C, D, and E here. They have masses between 5 to 10 times that of Jupiter. And when we track them over time, we go back year after year, we can actually see them orbiting the host star. Now, there are really wide separations here, about 15 to about 70 times the Earth-Sun distance, so really wide orbits. But you can see them moving a little bit over time. And when you do that, you can actually measure or constrain their orbital periods, their eccentricities, their orbital parameters. And some of the interesting results are that they appear to be coplanar in the system, so they probably formed in a disk, as we might expect. And the period ratios, so the ratio of the orbital periods of planet E to D to C to B is something that we call mean motion resonance. So every time planet E goes around once, planet D goes around twice, planet C goes around 4 times, and planet B goes around 8 times. And so these are 1 to 2 to 4 to 8 mean motion resonances. And we see the same thing with the moons of Jupiter. 3 of the moons of Jupiter undergo these same 1 to 2 to 4 resonances. This is a result of long-term dynamical evolution of these planets. So we're learning a lot just by imaging even a few systems. And we're not just imaging them, we're now at the point where we're taking spectra of their atmospheres. So we're learning about their basic chemical compositions. We see methane, carbon monoxide, water, cloud structure in many of these planets. And we now have about 20 or so planets have been imaged. So this is just a gallery of some of them. I don't have time to talk about them in detail, but I will just mention that many of them have been found by researchers at UT, including myself. So where do we lie right now with direct imaging compared to the rest of the exoplanet community? So here's a plot showing the mass of known planets versus separation. And this is normalized to that of Earth. So Earth is at 1 here and at 1 AU. So 1 Earth mass, 1 AU. These are planets found through the transit technique, where light is periodically blocked from the host star. The radial velocity method, which measures the back and forth wobble motion of stars. You can see that there are planets that basically go all the way down to the mass of Earth. So for direct imaging, we're not quite there yet. We're kind of bottoming out right now at about a Jupiter mass. And what we really want to do in the future is get to closer separations and much deeper masses to be able to image, again, Earth-sized planets. And to do that, we can get part of the way there with telescopes that are either planned or being built right now. I'm sure many of you have seen some of the photos of the James Webb Space Telescope mirror, which is now fully assembled and absolutely gorgeous. We have 3 30-meter telescopes that are either in the process of being built or are still undergoing some site selection. So the 30-meter telescope, the Giant Magellan Telescope, which the University of Texas is a founding member of, and the European Extremely Large Telescope, which is 39 meters. I know, the names are terrible in astronomy. And then we also have WFIRST here. This is a dark energy and exoplanet imaging mission, which is scheduled to launch in the mid-2020s. Now, there's a great backstory to this telescope. This was given to us, to NASA, by the National Reconnaissance Office, which is an intelligence agency of the United States, if you've never heard of it. And there's this great quote by a writer for Popular Science. If telescopes, and by the way, this is basically a Hubble analog, so 2.4 meters. If telescopes of this caliber are languishing on shelves, imagine what they're actually using. And these telescopes are not pointed at space. They're not studying astronomy for fun. They're pointed down at Earth. So what we really need to image Earth-sized planets are space telescopes, large 10 to 12 meter diameter space-based telescopes. One design for this incorporates what's called a star shade, so it looks like a flower. And this is a way of controlling the diffraction pattern of the star that you're pointed at. So instead of it being sort of a maximum and then a bunch of minima and maxima that go down, just like I showed you before, the petals here are constructed to perfectly cancel out and create a minimum right where the position of the star is, so that anything off axis from that star will shine through. So then the idea is to get an image like this, where you completely cancel out all the light from the host star, and anything off axis comes through. So there are so the way this works is right now, any kind of mission like this will be a multi-billion-dollar program. It'll be a flagship mission that may be launched in the 2030s. So we have to do a lot of planning in advance to get that kind of money and that kind of momentum to actually build something like this. So right now, there are 4 telescopes being considered for this flagship kind of program. One is an X-ray telescope. One is an infrared telescope. One is called HABEX, which is specifically designed to find exoplanets with direct imaging like this. And another is called LUVOIR. It's kind of like a Hubble on steroids, a 10 or maybe 15 meter Hubble telescope. And with at least 2 of these 4 designs, part of the main mission is to image planets. So this really is a direction that NASA may want to go. So these are under consideration. They'll be recommended to a decadal survey panel, and then they'll make recommendations to NASA. So we have, with equal priors, we have a 50% chance of getting one of these through. And again, it's not just to image planets, it's to study their atmospheres. So what we want to do is be able to tell the difference between an Earth-like spectrum or maybe that of Venus, which is dominated by carbon dioxide. Here on Earth, we also have CO, but we have water, ozone, methane, and many other species. We may also be able to identify biosignatures, which are spectroscopic features caused by life, usually in the form of metabolic byproducts. So that includes oxygen and a photolytic byproduct of that, which is ozone, O3, nitrous oxide, methane, something called the red edge in the optical spectra of our Earth, which is caused by chlorophyll. So you can actually detect signatures of chlorophyll from plants in our own spectrum, carbon dioxide, and even I've seen papers on pollution, potential pollution in exoplanet atmospheres caused, for example, by chlorofluorocarbons, also known as freon. But the best biomarkers are those that are in chemical disequilibrium, which means if you put some of those molecules in the atmosphere, they'd go away on really short time scales. So that means that it's regenerated. We also want biosignatures that are unique and can't be caused from geological processes, like carbon dioxide from volcanoes and even carbon dioxide. And we want them to be easily detectable. Now, there's also the prospect of monitoring these planets for a long time. And when we do that, we can get something called longitudinal phase mapping. So as these features come and go, we might be able to distinguish continental structures, in longitude at least, from oceans. And so this is actually a reconstructed image of the Earth from real data. There was a mission that went out, and when it was done doing its basic science, it turned around and observed Earth in many filters. And this is the kind of longitudinal map we might expect one day to get for rocky terrestrial planets orbiting other stars. And we might also see seasonal variations. So I'll leave it with this final image going back to the Voyager mission, the pale blue dot, and I'll open it up for questions. Thanks.
I'm here, I swear. Good job. All right, questions? Go ahead.
I'm kind of wondering about the, was it HR 86?
8799.
8799?
Close, yeah.
You mentioned that the A, B, and E, and E planets, the A being the farthermost, and then the most end. You talk about how they travel one time around, two times around, four times around.
Right.
The one you said was going the fastest was the one that was
Okay, so the question is about the HR 8799 system and the various orbital periods. So planet E, because it's closer in, goes much faster than the other planets further out, right? So the ratio of the periods is 1 to 2 to 4 to 8 going outwards. Yeah. Yeah, so E, the closest one in, orbits at a faster rate. Thanks.
I have a piggyback question on that one.
Sure.
You said there was another system that was like that. Is that something we see commonly or just coincidentally in those systems?
That's a great question. So how common are these?
Can you repeat that?
Yeah. How common are these mean motion resonances among exoplanets? So the other one that I showed, that was for the Galilean satellite. So the dominant moon's orbiting Jupiter. So we see it there. We see these kind of resonant structures all throughout our own solar system. Some of them reinforce each other. So you get you basically get moons or even planets that are have low integer period ratios of each other, but you also have ways to cancel them out. So you have gaps, for example, in the asteroid belt caused by the same kind of mechanism. And in planetary systems, we see the same thing. So especially with data from Kepler, which was rich, and we found thousands of planets so far. Many of them are in multi-planet systems, and most of those are in mean motion resonances as well. Yeah. So it is a very common phenomenon.
And question up top.
How do you track out the sun from the planets? It seems to me you can do a Fourier transform that vessel function, right? Can you put it in some sort of phase filter?
Yeah, so the question is about how we actually get rid of all the light from that host star. If we knew the exact point spread function, so if we knew exactly how it behaved, then we could just simply subtract it off. The problem is these speckles, they're called residual speckles, these come and go on very short time scales. So if you take lots of images one after the next, you'll see them coming and going and moving around. And it's caused by aberrations, imperfect AO correction, and imperfections in some of the quality of the optics. So we don't have an analytic model to subtract out like that. We have to use generally the data itself as a reference, and we have to make the planet somehow move relative to those speckles. So I won't go. There are lots of techniques that have been developed, including using principal component analysis to do this kind of work. But yeah, it's an active area of work to try to remove this, and it's really only over the past 10 years or so that we've had methods that are good enough to actually image planets with.
In the back.
Yeah. What are the benefits and limitations of using an array of telescopes to have a larger area versus taking one big telescope?
Okay, so the question is, what are the advantages and disadvantages of using an array of telescopes to image planets? So from the ground, at least, you can get basically better spatial resolution with a wider baseline if you use lots of small telescopes. I think what you're kind of leaning towards is an interferometer. And so it's a way to combine light from multiple telescopes. The Keck telescopes, so if you've seen Keck Observatory, there are two of them that are basically identical. It was once part of its main motivation to build two identical telescopes was to make it an interferometer, and you can get to very small separations that way. The problem is, yeah, you're not collecting all of the area, and it's very difficult and costly to do. So if we had enough funding, we could do this, and there is a lot of motivation to do this to image planets from the ground. There are also concepts in space of using a flying array of telescopes to do the same thing. So most of this boils down to funding and finances with a limited budget that's, let's say, temperamental on short timescales. So to continuously fund this kind of program, you need basically $1 billion mission or more. So it's really about cost. But generally, yeah, the more telescopes you have and the better you can link them up, the better for imaging planets.
Right here.
Talking about how few telescopes we have, how hard is it for researchers to buy time on these telescopes, and how does that work?
That's a great question. Okay, so how do we get telescopes? There are a limited number of telescopes. How do we get telescope time? So there are a couple avenues. The US, fortunately, the NSF funds the NOAO, National Optical Astronomical Observatory, which buys some of the time on the biggest telescopes. So that's how we as researchers generally can get time, unless you have institutional access. If you're a founding member of one of these telescopes, for example, the Keck telescope on Mauna Kea in Hawaii is owned and operated by Caltech and the University of California system and a couple other smaller partners. If you're part of that system, you get direct access that way. Otherwise, you have to go through this national route. And it's more competitive and more difficult, but we do have that route to do it. Yeah. And of course, here at UT, we have McDonald Observatory. So.